All right, so Jane has moved on from her atomic chemistry set after turning her dad into a radioactive man. She's decided to sort of focus more on the conventional chemistry aspect, which don't involve changes to the nucleus. Really what we're looking at is movement and changes to the way the electrons are arranged. Of course, what are you going to do with chemistry except make fireworks? Nothing better than that. So what we need to do is we need to, for Jane to be able to go through and actually do this to make different types of fireworks, she has to know what we call different types of chemicals. Okay? So step number one in being able to conduct chemistry and able to do stuff that we want to do is you got to know the names for what's the chemicals you're working with. So what we're going to focus on today is looking at nomenclature. How do we name things so that we can talk together in this room? You can talk with other chemistry students. You can talk with anybody around the world. And we have this unified system of how do we name things. And the reason why it's unified is that there's an international standards organization, the IUPAC, the International Union of Pure and Applied Chemistry, which is an international standard setting body that sets up the rules for how we name things. Okay? So we're going to go through and learn some of the rules that they use so that we can talk to other chemists and we'll all be speaking the same language, which is sort of like English, but really, in a sense, right now is a foreign language class where I'm going to teach you a ton of vocabulary and a little bit of grammar. Okay? So if you kept that sort of in mind, might give you a good mindset for where we're going here. All right, so first step, how we name something depends a lot on what it is. Okay? How we name a molecule or a compound depends a lot on how it is held together. Okay? What type of compound is it? If we think about the periodic table, elements on the periodic table break down into two very large categories. Okay? The first category is what we call the metals. Okay? Metals on the periodic table are everything to the left of the sort of big staircase that you see on most periodic tables. There's that thick dark line that indicates the staircase. Everything to the left of that staircase, all these elements from lithium on down to polonium and all these transuranics down here, those are all considered metals. They have certain characteristics, primarily having to do with how their electrons are arranged. They tend to lose electrons. They tend to form positive charges. Those are what we call the metals. Now, the stuff on the right, this little group of elements over here on the right of the staircase, these are what we call the non-metals. Okay? Non-metals. Non-metals tend to form negative charges. That is, they gain electrons during chemical reactions. And it is the combination of the non-metals with the metals, the transfer of electron from one to another, that we call an ionic compound, because they are held together with ionic bonds. Ionic bonds are bonds that are formed when we have ions, an element that has gained or lost electrons. So if I have a calcium atom and a chlorine atom, they both start out neutral. Okay? Two neutral atoms. If they come into contact with each other, what can happen is the transfer of electrons. The sodium will lose its electron. The chlorine will attract it and pull it away from the sodium. And that we will form a charge. The electron here in the sodium will be transferred to the chlorine. Okay? And we will form a sodium ion and a chloride ion. Okay? This is salt. Table salt, sodium chloride. Okay? Salt, the word salt in chemistry is a much more generic term than you're used to. In chemistry, a salt is not just sodium chloride. A salt is any kind of ionic compound. Okay? So I can have a salt of lithium, lithium salts. I can have potassium salts. Salts, ionic compounds formed with potassium. The word salt, in this context, in chemistry, means ionic compound. So, here I have a positive ion. We call that a cation. Okay, positive ions are called cation. Negative ions are called anions. Okay, positive ions are cations, negative ions are anions. I don't have any really cool little mnemonic for that. If you come up with one, share it with the rest of us.
So ionic bonds are metals and nonmetals?
Ionic bonds are formed by metals and nonmetals. Exactly right, and a very important distinction. That is your first cut at trying to name something. If I give you a compound, you say, hey, look, that has a metal and a nonmetal. Metals will always be listed first. The cation is always listed first in the name. The anion comes second. So we would name this sodium, and then this is chlorine, right? But we change the name of the element when it forms a compound. The anion name is changed from its root, chlorine, we change to chloride. Okay, we remove the original ending and stick an "ide" ending on there. So you can have chloride, oxide, fluoride, bromide, nitride, okay, sulfide, phosphide. We take the root and we stick on an "ide" ending instead. Question? For the anions, it's always "ide." For if you have just an element, there's more complexity here that we're going to get to. But if you have an element that it functions in this type, this ionic bonding, with a single element, then you change the name to an "ide." Okay? So I could give you a whole host of these guys to practice. All you have to do is look at the metal, the positive one, write down its element, take the negative anion, look up what its name is, change the ending to "ide," and you're done. Sodium chloride. Okay? That's the most straightforward, simplest sort of naming we do. There are additional levels of complexity, however, because the world is not just made up of ionic compounds, what we call binary ionic compounds with just two elements. Sometimes we have more complex situations, what we call type 2 ionic compounds. Some elements, particularly when we look on the periodic table, these guys in the middle here, okay, all these guys in the middle, what we call the transition metals. These transition metals are the ones in the middle here, and bleeding down into these metals down here. These metals do more complex chemistry because of the way their electrons are arranged in more shells and more complex situations. So something like iron will form a +2 charge. Iron typically forms a +2 charge, or it'll form a +3 charge. So iron will form multiple stable charges. Some elements form a 2 and a 3, some form a 1 and a 2, some a 3 and a 4. There are lots of different things that they can do. Some elements will form lots of different ones. Okay? Chromium, for instance, will form a 2, a 4, a 6, right? And many of you have probably heard of chromium with a +6 charge. If you've watched the movie Aaron Brockovich, for instance, hexavalent chromium means chromium with a +6 charge. That's all it means. So they do this when they run into other elements, like oxygen, for instance. Iron oxide is iron combined with oxygen. And remember, see that oxygen became oxide? But we need to distinguish between these two, because if I just write down iron oxide, I have no idea whether it's a +2 charge or a +3. And knowing the charge is critical for being able to write down the chemical formula. Because in ionic compounds, the charges are going to balance out. So when we write down the names, when we write down the words, we have to explicitly say what is the charge on this iron. And the way we do that is with Roman numerals. So iron with a +2 charge is written as iron, Roman numeral 2. What does this Roman numeral 2 mean? It means that it has a +2 charge. It does not mean that there are two irons. The Roman numerals tell us what charge does the metal cation have. Okay? So iron with a +3 charge would be iron with a Roman numeral 3. Now, there's another layer of complexity that we can add. Okay? this is type 2. That's the important type 2 metal cations. They form multiple charges. We have to write down what charge they have when we're using their names. When you're writing a chemical formula, you don't have to worry about that because you can figure it out what charge they have based on the fact that the charges are going to balance. They don't. The metal cations form positive because they're cations. Okay, so we don't have to worry about the negative. Yeah. All right, so we've talked about oxygen. This could be iron 2 oxide. But the world would be a pretty boring place if there were only single element compounds. A lot of times elements will react together in a different way. They will share electrons, what we call a covalent bond. But a group of these atoms sharing electrons could also form an ionic compound. So for instance, this compound, sulfite, sulfite, is a sulfur chemically bound to 3 oxygens with sharing of electrons, what we call covalent bonds, which we'll talk more about later. This sharing of electrons, this sulfite, also has a charge. It's also picked up 2 electrons. For instance, if it had reacted with an iron atom to gain 2 electrons from the iron, it would have the whole group of them would have a -2 charge. This is what we call a polyatomic ion. Poly means many, more than one. So polyatomic, more than one atom. Okay? So this is sulfite. This is sulfate. Okay? So ite and ate. Root is still sulfur. Ite and ate describe relative amounts of oxygen. So that this compound we would name iron 2 sulfite. And this one would be iron 3 sulfite. Okay? Sulfate. So sulfate, excuse me. Whew. Iron 3 sulfate. Okay? Now, here's the problem with this whole system. Okay? Ite and ate describe only relative amounts of oxygen. There are other compounds. For instance, nitrogen with oxygen. We can have a nitrite compound and a nitrate compound. Notice the same ite and ate ending. But a nitrite is NO2 with a -1 charge. And nitrate is NO3 with a -1 charge. Notice that here this ite was with 3 oxygens, and here the ate meant 4. In nitrogen compounds, the ite meant 2 would mean 2 oxygens, and the ate would mean 3. There is no easy rhyme or reason at this point for us to be able to figure this out. So it's going to be a purely memorization exercise. Okay? More flashcards will be required. If you take a look at the Mr. Glimmy sheet of things to remember, okay, which you should have picked up on your way in. The top left box lists the most common type 2 metal ions and the most common polyatomic ions. What does it say here? Mr. Glimmy's AP things to memorize. What should we do with this thing? Memorize it, okay? I promise if you didn't have to have it memorized, I wouldn't ask you to memorize it. Okay? You have to know these things. You have to know the name and the chemical formula with its charge. Because you have to be able to identify it either direction. If I give you the chemical formula, you have to know the name. If I give you the name, you have to know the chemical formula. Questions?
Is this all year or just one semester?
That's all year. This is the most important stuff to memorize all year long, for the whole year. Okay? So this unit, we're going to look at this box in the upper left, the ions, and we're going to look at the quantum numbers, and we're going to look at general periodic trends. That's what we're going to learn in this sort of unit. Questions? Excellent question. So here, right, there's a difference in the numbers here. And when I say the words, I said iron 2 sulfite, but there's not 2 irons. What does the 2 represent? The charge on the iron. This iron has to have a positive 2 charge because it is bound to this sulfite, which we know has a negative 2. So the positive and negative balance out. Now here, when we look at the iron 3 sulfate, again, the positive and the negative have to balance out, but now I'm balancing a plus 3 with a negative 2. 2 of the plus 3s gives me a plus 6. 3 of the negative 2s gives me negative 6. The positive and the negative have to balance out in ionic compounds. Okay? So for ionic compounds, we expect the positive and negatives to balance out. All right. Questions? Right. So the parentheses here indicate that I have 3 of this whole thing. This is a group that comes together. It's covalently bonded together. If you tried to put a 3 here, you would think something weird with just the oxygen. I want to indicate that I have 3 of these whole sulfate groups. All right? So you've got your Mr. Glimmy sheet of things to memorize. It's got a list of all these guys on it. Let's look at some problems. This is the example. Okay? So, name each compound. You need to look the name up on the periodic table if you don't know it. Notice the periodic table I gave you. This is a copy of the periodic table you will get on the AP test. That's why it says do not detach from book, and it doesn't have any names. This is literally from a copy of the AP test. This is the periodic table you'll get. Notice it doesn't have any names. They don't like you, so they didn't give you a periodic table with names. IB people, you're lucky for the IB test. You get periodic table with names and a whole fat information booklet. We'll talk more about that on Monday. So you can use the periodic table on the wall up here. If you have your binder reminder, that's got a periodic table. $55 is cesium. CS. Oh, how do you spell it? Yeah, cesium. C-E-S-I-U-M. Cesium. CS is number 55, cesium. C-E-S-I-U-M. So F is fluorine, which becomes fluoride. No? Hydrogen becomes hydride. I'll talk about that compound. This is a special compound. Yeah. B? Al is aluminum. And what's Cl? Chloride. Aluminum chloride. Aluminum only forms one charge. So far, the only thing we've talked about is does it form more than one charge. We don't have to describe how many of these chlorines there are because we can figure that out based on the charges. So aluminum chloride. When you're doing ionic nomenclature, you don't need to worry about how many there are unless you're trying to figure out what the charge is. In this case, for all these formula ones, we don't need to do anything except write down the name. Question? Number 80 is mercury. Yeah. Lithium hydride. Exactly right. Hydride. The hydrogen, the gen ending, drops off to become ide. So have you heard of lithium metal hydride batteries? They're a type of rechargeable battery, as opposed to like a lithium polymer, or there are various types, but lithium hydride. Yeah, you got to. What charge does the iron have? How do you? That's 2 is how many there are. You have to think about it. What charge would the oxygen have? We got to think about that. We got to know it. So, some really good points here. Okay, cesium fluoride, aluminum chloride. Okay, those are pretty standard. Again, we don't have to worry about how many there are, except if we need to figure out charges. Lithium hydride. A hydride is a special type of compound. Hydrogens don't normally form negative charges, right? If we look at where hydrogen is on a periodic table, based on where it is, it looks like it's kind of in the middle. But hydrogen's sort of a tricky one that can do multiple things. So hydride is a special form of hydrogen that has a negative charge. That's why you're not used to hearing it. Mercury oxide. Okay, there's multiple forms of mercury here. What charge does the mercury have? Well, we got to be able to figure that out. There are a few rules that will help us. Okay? If you look at the periodic table, take a sec and look at the periodic table, either up here on the wall or on your thing. The first column on the periodic table, elements in this first column almost always form a +1 charge. Okay? Elements in the first column form a +1 charge. Memorize that. Second column on the periodic table, these elements form a +2 charge. Okay? Second column, they form a +2 charge. See all these guys in the middle? It's crazy. Okay? Goes all wonky. They form lots of different charges. Those are primarily our type 2 metal cations. Okay? Those are mostly our type 2 metal cations, with a few exceptions. Okay? Zinc forms a +2 charge, and silver forms a +1 charge. Now we come back to the other side here. See this last row? No charges, noble gases, unreactive, don't form compounds. Second to last column, the fluorine family forms a -1 charge. So second to last one, -1 charge. Oxygen family forms a -2 charge. And the nitrogen family forms a -3 charge. Carbon is special, typically doesn't form any charge at all. Boron and aluminum, these guys form a +3 charge. So it goes +1, +2, +3, -3, -2, -1.
Which is a +3?
+3 is going to be the boron, aluminum, gallium. Question?
When you were saying, like, for instance, in the row with oxygen, the column with oxygen, does that go all the way down to
Tellurium, selenium. Down here, the lower you go, the less accurate these kinds of rules become. The more complex the electrons become, the less accurate, particularly over here when you start to get around this border region.
At that point, does, like, the staircase matter?
The staircase matters because elements near the staircase are typically called metalloids. They have properties of like metals and nonmetals, and that includes what charges they form. So it's a little bit more complex than a nice simple rule. For now, we'll pretty much stick with the higher ones. So this is important because if I know that oxygen has a -2, what charge does this mercury have to balance it out? It has to be a +2. +2 balances out -2. So that means this is mercury 2 oxide. Now, if I'm looking at the next one, this is where it gets a little interesting, right? I have Fe2O3. What charge do we say oxygen forms? So that's a -2, but there's 3 of them, so that's -6 altogether. Iron has to balance that out. So all the irons altogether have to sum up to +6. There are 2 of them. What charge does each one have to make this work? It's got to be a +3. +3 times 2 gives me +6. +6 minus 6 balances out. Okay? So oxygen is just going to be oxide, but the iron has what charge? So this is iron 3 oxide. Sodium, and you just have to recognize this, NO3 is a polyatomic ion. We have to name it as a polyatomic ion, which means we need to look it up. That is a sodium nitrate. 8 ending, because this is NO3, that's nitrate. The ending here describes to us how many oxygens this compound has. Because this is, the difference is this nitrogen and oxygen are chemically bound together in a different way. They're held together by covalent bonds, but the whole group of them has a charge. As opposed to, this is a positive and this is a negative. This whole thing right here is a -1 charge.
Wait, so then in the sodium nitrate, we have a -7 charge, right?
Nope. The NO3, this compound, NO3, has a -1 charge. That whole thing has a -1 charge. Chemically, we can write that down as nitrogen bound to 3 oxygens. With this whole thing, I did it. This whole thing together has a -1 charge. And we're going to learn all about this in a couple of weeks. Okay? Oxygen has a -2 charge when it's by itself. Okay? When it's by itself.
On my periodic table in the planet, it says aluminum. You wrote aluminum.
Aluminum is English, American English correct.
So it doesn't matter if you write it.
No, it doesn't matter. British do it differently. And why they would use the British spelling instead of the English spelling, I have no idea.
Mr. Fleming,
Yeah.
so for sodium nitrate, the nitrate, there's nitrogen, which has -3, and then
Right, here's the key. You can't do that. This is a group. This nitrate has a -1 charge, and you just got to memorize it. You can't treat this as nitrogen and oxygen. It's a nitrate group all stuck together.
why does it have
Nitrite would be NO2, and it has a -1 charge. Yeah.
so they both have -1?
The whole group has a -1 charge. Okay, treat it as a group, and we're going to learn how they're bonded internally. It's different than what we're talking about. So yeah, let's go over here. Hydrogen fluoride. We want to write down the chemical formula here, right? Hydrogen fluoride. What charge does hydrogen make? Right? Hydrogen is going to be a +1 normally. It's in that first column. Fluorine is going to be a... So we're going to need one of each. Okay, one of each. HF, balanced charge. When you're changing the words into formulas, you've got to think about balancing the charge. Okay? So, aluminum has what charge? +3. And this is nitride. Nitride. Nitride is going to be just straight up nitrogen by itself. What charge? +3, -3. We just need one of each. So far, easy peasy. Lemon squeezy. So, lead 4. Uh-oh. Mr. Gloomy went crazy. What does this 4 here mean? Means that the lead has a +4 charge. So if we were writing this down, if we were thinking about writing this, the Pb, the lead, would have a +4 charge. Oxide means oxygen, which has a negative. Look where it is. It's not in the 1 column. It's in the -2 column. So it's going to have -2. So I need to balance out the +4 with the -2. I need 2 oxygens. 2 oxygens for every 1 lead to balance out the charges. PbO2. The subscripts here tell me how many of each element, how many of that element that it's next to do we have. It's a ratio, yeah. For every, in lead oxide, you have 2 oxygens for every 1 lead. In these ionic compounds, they're actually big crystals. We'll talk about that in a little bit. All right, magnesium sulfate. Magnesium, Mg, has what charge? Second column on the periodic table tells me it's a +2. Sulfate, wait a sec, it's It's got an 8 ending. It's not an "ide" ending. That means I got to look it up on this thing. I got to know it. There's no other way. So sulfate is SO4, -2 charge. +2, -2, they'll balance out nicely.
Well, I need a 4.
This sulfate, when somebody says sulfate to you, you think SO4. Sulfate, the word means sulfur with 4 oxygens grouped together, sulfate, SO4. Always going to be 4 oxygens by definition. Now, what if I needed 2 groups of sulfates? Then I'd have to put parentheses around this and put a 2 like that. Question? No. Question? Ian?
Yeah. So, do most of the ites and the eights have, does that mean there's oxygen?
Yes, ite and eights mean that there's oxygens. There's other ones too, like hypochlorite, perchlorate. There are other words too, if you look through there. All right? All right, that's it. That's ionic compounds. That's pretty much all we need to know about ionic compounds. We're going to have to practice this because it's got to be completely automatic. Okay, this is the fundamental vocabulary that we're all going to use. We can't spend time looking a lot of this stuff up every time we need to use it. So it's going to have to be practiced. It's going to have to become instinctual, which means we got to do it over and over and over. That's not fun, but it is necessary. Okay? Now, this has all been about ionic compounds, right? And I've mentioned this word covalent compounds a couple of times. Covalent compounds have a whole different naming system. Okay? In some ways, much simpler. Okay? Less memorization. So, covalent compound, for instance, this nitrogen atom here could be covalently bonded to an oxygen atom. The covalent bonding is the sharing of electrons. Sharing of electrons between the 2 atoms. We're going to do a whole unit on it. It's our next unit, chapters 8 and 9. We're going to do a whole unit on how this works. Covalent bonding means sharing of electrons. Covalent bonding takes place when you have 2 non-metals. So nitrogen and oxygen, there's no metal involved here. Covalent bonding is non-metal, non-metal. Ionic bonding, metal and non-metal. Okay? With with a couple of small exceptions. Metal bonds are called metallic bonds. Not something we're going to worry a whole lot about. They are a special type of bond that we'll talk about a little bit in chapter 8 and 9. No special naming. We don't have to worry about that.
Are there alloys?
Yeah, alloys are in many senses mixtures, but they can also because of the way the metallic bonding works, it's special. It's a delocalized covalent bond. We'll talk about what that means next, chapter 8 and 9. So, NO, right? 1 nitrogen, 1 oxygen. But you know what? There are lots of different types of nitrogen-oxygen compounds with lots of different ratios of nitrogen and oxygen. For covalent bonding, because there's no charges, this compound doesn't have any charges. The nitrogen is neutral, the oxygen is neutral. We have to explicitly say what the ratio is. So to name this, we say nitrogen monoxide. And the mon means 1 oxygen. So if I had this compound, a nitrogen with 2 oxygens, I'd do the same thing. Again, the first element that is listed, N, becomes nitrogen, and now I would have dioxide because there are 2 oxygens. Now, what if I reverse this? What if it's 2 nitrogens and 1 oxygen, N2O? Yep, the nitrogen here, when it's a mono, when it's 1 by itself, we don't have to worry about putting the mon. We never put that for the first element. But if there's more than 1, we do put the di. Dinitrogen monoxide. Okay? Huh? It's a little complex, but it has to do with some chemical properties that we don't know about yet, called electronegativity. We'll get there. Yep, I am. If I didn't already, I should have. It's in the textbook, and you will need to look them up. Sorry, I should have put on the Mr. Glimmy things to remember. Mono, di, tri, tetra, penta, hexa, sept, oct, non, and dec. It's in the textbook in chapter 2. You can look it up. It's pretty straightforward. Most important are like 1, 2, 3, 4, and 5. And then for organic chemistry, we'll talk about some more. So this is NO3, which would be nitrogen trioxide. Nitrogen trioxide. All right? Yeah, this is easy because you don't have to worry about figuring out charges. You just have to count. You can count. We can all count. And then you have to convert the number into the special word. Mono, di, tri, tetra, hex. What's 5? Penta. Hex is 6. Sorry.
Is this like
Tetra.
they're built because of the valence electron?
Yeah, it's all about the valence electrons. We're going to learn all about that in gory detail soon. All right, let's practice a few of these. This is your second example box. Again, do I need to worry about charges? Why not? Covalent bonds have no charges. Covalent bonds have no charges. So, C, carbon, how many fluorines are there? 4, which we use tetra, carbon tetrafluoride.
What's 3?
Tri.
What's 5?
F-L-U-O-R. Again, notice the second one still gets this "-ide" ending. So we still stick the "-ide" ending on here. The "-ide" ending still goes, just like we did for the ionic compounds.
What is 4?
Tetra.
Oh.
So N2 is going to be dinitrogen, 4 tetroxide. So what's this one look like? Nitrogen trihydride or ammonia? So ammonia is one of the few non-systematic names that we still use. Ammonia and ammonium. You'll notice there is a polyatomic ion called ammonium. This is the covalent compound ammonia. Just like if you thought about, say, this compound, how would you name that compound? H2O. Dihydrogen monoxide or water. We're going to call that water. Okay? The systematic name is not used. Okay? Did you notice that I've just given you the answer to B? So dihydrogen monoxide, if somebody says, hey, watch out for that DHMO, that dihydrogen monoxide, it's a killer. Kills probably more people than any other chemical in the United States. How many people drown each year? Okay? There are some pretty funny websites out on the web where you can look up dihydrogen monoxide or DHMO. There's all this scary stuff. How come the government doesn't regulate it more? How come we're allowed to have it in our homes?
So when you say like hydrogen peroxide?
Peroxide. Peroxide is a polyatomic compound, polyatomic ion. A peroxide is 2 oxygens with a -2 charge. That's a polyatomic ion. So you can have lithium peroxide, hydrogen peroxide, and that would be, this has a -2 charge, hydrogens would have a +1, so you'd have H2O2. The peroxide is 2 oxygens with a -2.
Why don't you call hydrogen peroxide dihydrogen peroxide?
Because it's actually an ionic compound.
So
It's much more like an ionic compound. All right, so we did the carbon dioxide is CO2, dihydrogen monoxide, H2O. Yes, there is homework. Of course there's homework. Don't leave without writing down the homework. Okay? Where's my homework packet? Good thing you got the weekend. No, not that many. It's only a few.
But I thought you said good thing you had the weekend. It's super long.
Well, you might want to check out 69, 71, and 73. That's it. That's enough. I know it doesn't look like it. Some of those problems go A through I.